Hello all. So we'll continue. In the last lecture we have studied how a continuous AWGN channel can be converted to an n-dimensional vector channel, where this n-dimensional vector channel as vector x is equal to sk plus n, where each of these vectors are of n dimension, and this n-dimensional space is spanned by our basis functions phi j of t with j equal to 1 to capital N. So we have studied it. Now consider the vector n. N is actually n1, n2, etc. nn, or nj, j equal to 1 to n. So it contains capital N random variables which are Gaussian distributed and which are independent. We have proved all these. So it is called IID, Gaussian random variables, which means in independent and identically distributed Gaussian random variables. Each has a mean E of nj equal to 0 and variance E of nj square, which is equal to n0 by 2. So that n0 by 2 we get from the covariance. Covariance E of nj and k is actually n0 by 2 delta of j minus k. So it has value only when j equal to k, and its value is n0 by 2. Now you have capital N independent and identically distributed random variables. So its PDF, probability density function, will be, when the random variables are independent, to find the PDF you have to multiply the individual PDFs. So the PDF is given as pi j equal to 1 to n 1 by root of 2 pi. That is the equation of a single Gaussian random variable, 1 by root of 2 pi sigma square e raised to minus x minus mu the whole square by 2 sigma square. So here mean is 0 and variance is n0 by 2, and arranging, so you will get it as 1 by pi n naught the whole raised to n by 2 e raised to minus mod n, or norm of n the whole square by n naught. And norm of n is actually root of n1 square plus n2 square, etc. nn square. So it is the sample length of the noise vector. Okay. So it is actually the length of the noise vector from the origin, root of n1 square plus n2 square, etc. nn square. So we are dealing with n-dimensional signal space or n-dimensional space. It is actually extension of our 2D. So our 2D equations are also extended. So we have got x equal to sk plus n, and what we have seen is that this vector n has a PDF, or probability density function, which depends on mod n or norm n square. The norm n represents the vector, the length of the vector from the origin, or we can say that it is having a spherical symmetry. And the sk is a deterministic vector. Sk is deterministic. So this means that x, the vector x, also will have the same distribution as n, but around sk. So our n is having Gaussian distribution, symmetric. It is symmetric, or it has spherical symmetry, but it is around 0, mean is 0. So here you have a value sk, or vector sk, which is a deterministic value. So that means the the received signal x or received vector x will also have a same distribution as the noise, but it is around the vector sk. So we can consider the vector x as a scatter region around the signal point sk. This x is having a random distribution. അപ്പോൾ എസ് കെ എന്ന് പറയുന്നത് വളരെ ഒരു n ഡയമെൻഷണൽ സ്പേസിലൊരു പോയിൻ്റാണ്. എക്സ് അതിന് ചുറ്റും സ്പെറിക്കലി വരും. ഓക്കെ, സോ എ സ്കാറ്റർ റീജിയൻ ഈസ് ഫോംഡ് അറൗണ്ട് ദ സിഗ്നൽ പോയിൻ്റ് എസ് കെ. We have capital M signals, so obviously there will have M. We will have M scatter regions corresponding to each of the M input messages. Now by analyzing the position of the received vector x, we can decide on the transmitted message, and obviously since there is noise, there is a chance of error, and the probability of error is represented as PE. So here I have shown an example. So we can't draw this n dimensional space, so I have drawn a 3-dimensional space. So you have 3 axes, phi 1 of t, phi 2 of t and phi 3 of t. So capital N is 3, number of orthogonal basis function, and number of energy signals or sk of t is 4. Capital M is 4. So I have represented the points S1, S2, S3 and S4. Now you can see that if we are if we are considering a 3D plane, this is actually the norm of S4, or it is the length of each of the point from the origin. So this is our signal space. This is a 3-dimensional signal space, and we are considering capital M equal to 4 energy signals. So these are our messages. അപ്പോൾ എന്ന് പറഞ്ഞാൽ നമ്മൾ അയക്കാൻ ഉദ്ദേശിക്കുന്ന മെസ്സേജ് 4 മെസ്സേജാണ് നമുക്കുള്ളത്. M1, M2, M3, M4. അത് S1 of t, S2 of t, S3 of t, S4 of t എന്നുള്ള 4 ഫൈനൈറ്റ് ഡ്യൂറേഷൻ എനർജി സിഗ്നൽസിലേക്ക് മാറ്റും. അടുത്ത ഗ്രാം ഷ്മിറ്റ് പ്രൊസീജിയർ വെച്ചിട്ട് ഈ എനർജി സിഗ്നൽസിനെ എല്ലാം ഈ 4 സിഗ്നലിനെ നമുക്ക് 3 ഡയമെൻഷൻ വെച്ചിട്ട് റെപ്രസെൻറ്റ് ചെയ്യാം. ഇപ്പോൾ 3 ബേസിസ് ഫംഗ്ഷൻ ഉണ്ട്, phi 1 of t, phi 2 of t ആൻഡ് phi 3 of t. അപ്പോൾ അതിൻ്റെ മീനിങ് എന്ന് പറഞ്ഞാൽ ഈ 4 സിഗ്നലിനെയും 3 ബേസിസ് ഫംഗ്ഷൻ്റെ ലീനിയർ കോമ്പിനേഷനായിട്ട് എഴുതാൻ പറ്റും. അപ്പോൾ ഈ 4 സിഗ്നൽസും ഈ 3D സ്പേസിൽ ഓരോ പോയിൻ്റായിട്ട് മാറും, വെക്ടറായിട്ട് മാറും. അതാണ് S1, S2, S3, S4. ഇനി ഇത് ട്രാൻസ്മിറ്റ് ചെയ്തിട്ട് അതിലേക്ക് നോയ്സ് ആഡ് ആവും. നോയ്സ് ആഡ് ആവാൻ നേരത്ത് നോയ്സ് ഇൻഫിനിറ്റ് ഡയമെൻഷനാണ്. പക്ഷേ നമ്മുടെ ഡിറ്റക്ഷൻ പ്രോബ്ലത്തിൽ നമുക്ക് n ഡയമെൻഷനുള്ള നോയ്സ് മാത്രം കൺസിഡർ ചെയ്താൽ മതി, ബാക്കി ഇറലവൻ്റ് ആണെന്നുള്ളത് അത് നമ്മൾ നേരത്തെ പ്രൂവ് ചെയ്തു. സോ നോയ്സ് ആഡ് ചെയ്ത് വരാൻ നേരത്ത് വാട്ട് വി ഗെറ്റ് ഈസ് വി വിൽ ഗെറ്റ് സ്കാറ്റർ റീജിയൻസ്. നോയ്സ് ആഡ് ചെയ്തതാണ് കൃത്യമായിട്ട് ഈ പോയിന്റിലായിരിക്കില്ല വരുന്നത്, നമ്മൾ റിസീവ് ചെയ്ത് കിട്ടുന്നത്. അതിന് ചുറ്റും ഒരു സ്കാറ്റർ റീജിയനായിട്ട് ഫോം ആവും. സോ വിൽ സീ ദാറ്റ്. അത് ഈ ഇക്വേഷനിൽ നിന്നാണ് കിട്ടുന്നത്. നോയ്സിൻ്റെ ഡിസ്ട്രിബ്യൂഷനും റിസീവ് ചെയ്ത സിഗ്നലിൻ്റെ ഡിസ്ട്രിബ്യൂഷനും സെയിം ആയിരിക്കും, എക്സെപ്റ്റ് ദാറ്റ് നോയ്സ് ഹാസ് 0 മീൻ while the received signal has a mean of sk. So now we will draw the constellation diagram. So this is the extension of the previous signal. So we have 3 basis functions and 4 signals. So this dots around these signals are the received vectors, capital X. So you can see, since the value of noise is random, the received vector is displaced around the original signal point and it forms scatter regions. So here we have 4 scatter regions. Ideally, this Gaussian distribution, it extends up to infinity. There is a finite probability that this scatter regions or the value of this x can go anywhere up to infinity. The only thing is the mean will be S3. But you can see that the tail values in a Gaussian distribution will be having very low probability and the mean is having the highest probability. So our mean is S3. So the probability of observing the received signal diminishes rapidly as the point is scattered away from the center. അപ്പം നമ്മുടെ സെൻറ്ററിൽ നിന്ന് ഒരുപാട് ദൂരത്തേക്ക് പോയിൻ്റ് കിട്ടാൻ പ്രോബിലിറ്റി ഉണ്ട്, പക്ഷേ ആ പ്രോബിലിറ്റി വളരെ കുറവായിരിക്കും. ഗോസിയൻ ഡിസ്ട്രിബ്യൂഷൻ്റെ പ്രത്യേകതയാണ്. So you'll get something like m scatter regions. So this is one scatter region and this is another. So here you can see that this scatter regions overlaps. So this means that what I have sent is S3, but there is a finite probability that it is found close to S4 than S3. Okay. So അങ്ങനെ സംഭവിക്കാം. Everything depends on the strength or variance of the noise. Based on the variance of the noise, either the scatter regions can overlap or they doesn't overlap. Anyway, there will be capital M scatter regions. So you can have this idea in mind. ഇവിടെ നമ്മൾ ചെയ്യുന്നതെന്ന് വെച്ചാൽ എല്ലാ സിഗ്നലിനെയും വെക്ടർ ആക്കിയാണ് കൺസിഡർ ചെയ്യുന്നത്. വെക്ടർ നോയ്സും വെക്ടറാണ്, സിഗ്നലും വെക്ടറാണ്. റിസീവ്ഡ് സിഗ്നൽ എന്ന് പറയുന്നതും ട്രാൻസ്മിറ്റഡ് സിഗ്നലും വെക്ടറാണ്. എല്ലാം ക്യാപിറ്റൽ N ഡയമെൻഷണൽ വെക്ടേഴ്സാണ്. Now an intuition comes like the detection is very simple. What we can do is, if the received signal point is close to S1, S2, S3 or S4, we map the received signal point to the point which is, or the original signal point which is maximum close to the received signal point. എന്ന് പറഞ്ഞാൽ നമുക്കൊരു പോയിൻ്റ് കിട്ടിയാൽ അതിന് ഏറ്റവും അടുത്തുള്ള സിഗ്നൽ പോയിൻ്റ് ഏതാണെന്ന് നോക്കുന്നു, അതിലേക്ക് മാപ്പ് ചെയ്യുന്നു. വെദർ ഇറ്റ് ഈസ് പോസിബിൾ. അങ്ങനെ ഒരു ഇൻഡ്യൂഷൻ നമുക്ക് വരാം. ബട്ട് തിങ് ഈസ് ദാറ്റ് ഇറ്റ്സ് നോട്ട് കറക്റ്റ് ഓൾവേസ്. ഇറ്റ് ഡിപ്പെൻഡ്സ് ഓൺ മെനി അതർ തിങ്സ്. നമ്മളത് പഠിക്കും എന്തൊക്കെയാണ് നോക്കേണ്ടത്. നമുക്ക് നേരെ അടുത്തുള്ളത് തന്നെ എടുക്കാൻ പറ്റില്ല. ഇറ്റ് ഡിപ്പെൻഡ്സ് ഓൺ മെനി അതർ തിങ്സ്. Okay. So we will do a mathematical analysis. So detection. If you find a vector x closer to Sj, there is a probability that it has been generated by some other message vector Sk. So although this x is closer to Sj, but there is a probability that it has been generated by some other message vector. So if we are mapping Sj to x, then it results in an error. ഇവിടെ പറയുകയാണെങ്കിൽ ഈ പോയിൻ്റ് നമ്മൾ S3യിലേക്ക് മാപ്പ് ചെയ്തു. കാരണം S3ക്ക് അടുത്താണ് കിടക്കുന്നത്. പക്ഷേ അത് എററാണ്. കാരണം ഇറ്റ് വാസ് ആക്ച്വലി S4 അയച്ചപ്പോഴാണ് ഇവിടെ കിട്ടിയത്. പക്ഷെ നോയ്സ് കാരണം ഇവിടെ കിട്ടി. പക്ഷെ അത് S3യിലേക്ക് മാപ്പ് ചെയ്താൽ അത് തെറ്റാണ്. Okay. So this may result in an error. So the task of our optimum receiver is to decide from X which message was transmitted and obviously the error should be small. So the task of our optimum receiver is to decide from the received vector X which message was transmitted with minimum probability of error. So stated otherwise, we can divide the entire signal space into M disjoint areas, Z1, Z2, or M disjoint regions, Z1, Z2, etc., Zm. If X falls into distant region Zk, we will decide that the message transmitted was Mk. X എന്ന് പറയുന്നത് ZK എന്ന് പറഞ്ഞ റീജിയണിൽ ആണ് വീഴുന്നതെങ്കിൽ നമ്മളതിനെ MK എന്ന് പറയും. MKയിലേക്ക് മാപ്പ് ചെയ്യും എന്ന് പറഞ്ഞാൽ MK SK എന്നുള്ള സിഗ്നലാക്കി മാപ്പ് ചെയ്തു, അത് അയച്ചു. അപ്പോഴാണ് എക്സ് കിട്ടിയത്. അത് ZK എന്ന റീജിയണിൽ വന്നു. അത് കാരണം ഞാനത് MK ആണ് അയച്ചതെന്ന് ഞാൻ വിചാരിക്കാം. അത് ശരിയാവാൻ തെറ്റാവും. അത് തെറ്റാനുള്ള സാധ്യത മിനിമം ആക്കണം. അതാണ് ഒപ്റ്റിമം റിസീവറിൻ്റെ പ്രത്യേകത. അപ്പോൾ അങ്ങനെ റീജിയൺ ആക്കാൻ പറ്റിയാൽ our problem of designing the receiver reduces to choosing the boundaries of the regions Z1, Z2, etc., Zm. So problem of designing the receiver or optimum receiver. നമ്മൾ ഇത്ര റീജിയൺ ആക്കിയാൽ ഓരോ റീജിയണിൽ വരാൻ നേരത്തെ അതിലേക്ക് മാപ്പ് ചെയ്യാമെന്ന് പറഞ്ഞു. അപ്പം നമ്മുടെ പ്രോബ്ലം എന്ന് പറയുന്നത് ഈ റീജിയൻ്റെ ബൗണ്ടറി കണ്ടുപിടിക്കുക എന്നുള്ളതായിട്ട് ചുരുങ്ങി. You will see how these boundaries can be found out. So we will do a mathematical or statistical characterization. So here the most important thing is that the most important characteristic is the conditional probability density function fx of x given mj. So it's a PDF. It's a probability that we receive a particular vector x given I have transmitted a message mj. mj എന്ന് പറഞ്ഞൊരു മെസ്സേജ് അയക്കുമ്പോൾ എക്സ് എന്ന് പറഞ്ഞ ഒരു വെക്ടർ കിട്ടാനുള്ള പ്രോബിലിറ്റി അതൊരു PDF ആണ്. എക്സ് ഏത് വേണം വരാം. MJ അയച്ചാൽ നമുക്ക് എക്സ് എന്ന് പറഞ്ഞ കോമ്പിനേഷൻ n ഡയമെൻഷണൽ സ്പേസിൽ ഇൻഫിനിറ്റ് പോയിൻറ്റ്സിൽ ഏത് വേണോ കിട്ടാം. എക്സ് എന്ന് പറഞ്ഞാൽ ഒരു പോയിൻ്റാണ് n ഡയമെൻഷനിൽ. ഇപ്പോൾ MJ എന്ന് പറഞ്ഞാൽ അയച്ചാൽ we have seen that if we are sending a message, there is a fixed probability that each of the infinite points in the n dimensional space that we can get, and that depends on the message that we are sending and the noise also. So that conditional probability density function is the most important characteristic of an AWGN channel. So this leads to a functional dependence on x given that mj was transmitted using sj of t. So I have transmitted mj using the signal sj of t. What is the probability that I get a given x? I get x. But you have to understand that the receiver works in the opposite way. Receiver receives x or given x. What is the probability that a particular message was sent? Receiver works in the opposite way. Opposite probability ആണ് നമുക്ക് ആവശ്യം. പക്ഷേ ഇതാണ് നമുക്ക് നമ്മുടെ ചാനലിൽ പറയാൻ പറ്റുന്ന സാധനം. ചാനലിനെ ക്യാരക്ടറൈസ് ചെയ്യാൻ ഉപയോഗിക്കുന്നത് fx of x given mj. We have sent mj. What is the probability that we have received a particular signal or particular vector x, received vector x? So here I will use signal and vector interchangeably. So both are same. A signal is converted to a vector using the signal space concepts. So this fx of x given mj is called as the likelihood function. And we already know this for the vector channel x is equal to sj plus n. Sj is constant and noise vector is random. So obviously x will have the same distribution as n but centered at the point Sj. നേരത്തെ കണ്ടു. So by using the PDF of n, I can write the PDF fx of x given mj as 1 by pi n naught whole raised to n by 2. So this we have derived earlier. So our n was having a distribution as Gaussian with zero mean. So this likelihood function will have the mean as Sj. If mj is sent, the mean of the received signal is Sj. So we have seen in that picture also. If I am sending mj, you will get the received vector will have a Gaussian distribution, but the mean will be Sj. So this is the likelihood function. This is a probability that given mj or mj was sent, what is the probability of getting x? So it is a Gaussian PDF with mean Sj. Geometrically we have seen that in the previous slide. So this is exponential. So in practice we use log likelihood function. So log is a monotonically increasing function, so there is no issue of using a log likelihood function. So, and when we are using log, this exponential goes and we can work with non-exponential times. So that is this thing becomes simple. So coherent detection. The problem. Given an observation vector x, perform a mapping from x to an estimate m cap of the transmitted symbol mj in a way that you would minimize the probability of error Pe. So you get I have got a vector x. I need to estimate m cap such that the probability of error m cap എന്ന് പറയുന്നത് mj അല്ലാതെ വേറെ ഏതെങ്കിലും വരികയാണെങ്കിൽ അതാണ് എറർ എന്ന് പറയുന്നത്. So the probability. So we have got x cap, but it was not mj that was sent. So probability of error is probability that we have got x, but mj was not sent. So that is actually 1 minus probability that we have got x and actually mj was sent. Okay, so that is a problem. We need to minimize this probability. So the optimum decision rule, it is maximum a posteriori probability or MAP rule, says that set the estimated message m cap as mj if the probability that P of mj given x is greater than P of mk given x for all k greater than k not equal to j. Okay. So for all k's, probability of mj given x is greater. So what does it means physically? We have received as x and we are calculating the probability that the message was mj sent. So if I am getting the probability of a particular message given x greater than the probability of all other messages given x, then it is straightforward to decide that the message actually sent was mj. അതായത് എനിക്ക് എക്സ് കിട്ടി, അപ്പോൾ എനിക്കുള്ള എല്ലാ മെസ്സേജസിൻ്റെയും എല്ലാ ക്യാപിറ്റൽ മെസ്സേജസിൻ്റെയും പ്രോബിലിറ്റി കണ്ടുപിടിക്കുകയാണ്. ഗിവൺ വാട്ട് ഐ റിസീവ് ഈസ് എക്സ്. ഓക്കെ, അപ്പോൾ അതിൽ ഏറ്റവും വലിയ പ്രോബിലിറ്റി ഏതാണോ വരുന്നത് ആ മെസ്സേജ് ആണ് ഞാൻ അയച്ചതായിട്ട് ഡീകോഡ് ചെയ്യും. സോ അത് കറക്റ്റാണ്, ചിന്തിച്ചാൽ മനസ്സിലാവും. That is the optimal rule. That is called MAP rule. But the issue is we can't directly find this probability. So we'll have only the reverse probability, or that we have seen. We have the PDF of probability of x given mj. mj അയച്ചാൽ എക്സ് കിട്ടാനുള്ള പ്രോബിലിറ്റി എനിക്ക് കണ്ടുപിടിക്കാം. അല്ലെങ്കിൽ അതൊരു PDF ആണ്, അത് ആ ചാനലിൻ്റെ പ്രോപ്പർട്ടിയാണ്. ദാറ്റ് വി ക്യാൻ എസ്റ്റിമേറ്റ്. ഓക്കെ, so we will use Bayes theorem. You know it, Bayes theorem. So I can write the optimal decision rule like this. For all j's between 1 and m, I need to find the maximum value of p of mj given x, and I will select that message mj as my m cap, which gives the maximum value for this probability. But this probability is not straightforward. So what we will do is we will use Bayes theorem. P of mj given x is p of mj into fx of x given mj by fx of x. Now you can see that for all j's, whatever be the value of j, this is a constant. So this can be neglected. So I will write p of mj, and this value we have already derived before, 1 by pi n naught. So this is from fx of x given mj is actually Gaussian distributed with mean sj. We have derived it. So using that equation here, now we take log. So this is ln p of mj. This log of exponential is the exponent itself, and this is a constant. That is irrelevant. That we are, when maximizing, this constant doesn't have any significance, so that is removed. Then we are expanding this term. So n naught by 2 ln p of mj minus half x square plus inner product of x square plus, sorry, norm square of x plus sj square minus 2 into x dot sj. So x square is common for all j's, so it doesn't have any significance in maximization. That is also removed. And we know that this norm of sj square that we have studied in the first lecture, that it is the energy of the signal. Norm square is the energy. So argument max, so it is minus half j plus x dot sj, where ej is the energy of sj of t, and the other term is neglected. So we have got the MAP detector for AWGN as m cap equal to, we will maximize this term cj plus x dot sj, where cj is n0 by 2 ln p of mj minus half into ej. Now what is this p of mj? P of mj is the probability of our initial messages m1 m2 etc. m capital M. Now for a particular j, this term is constant, cj is constant, so that is why it is written as cj. And the MAP, for the MAP detection rule, what you have to do is you have to maximize the term cj plus x dot sj. Find that j. ഏത് മെസ്സേജ് എം ജെ ആണോ, ഇതിനെ മാക്സിമൈസ് ചെയ്യുന്നത്, ആ മെസ്സേജാണ് അയച്ചതെന്നാണ് നമ്മൾ എടുക്കുന്നത്. ദാറ്റ് ഈസ് അവർ ഒപ്റ്റിമം റൂൾ. ഓക്കെ, now consider that I have told that this p of mj is actually the probability of our input message or transmitted message. Now consider that all the messages are equiprobable. So you have capital M messages, so p of mj is 1 by capital M. Now if you are using that constraint also, then this MAP detection changes to what is called ML detection or maximum likelihood detection. Okay, so MAP detector plus an extra constraint, that is all the messages are equiprobable, that will give you ML detector or maximum likelihood detector. We'll see why it is called maximum likelihood detector. So ML detector. So actually the MAP rule was maximize P of Mj into Fx of x given Mj. Now if all the messages are equiprobable, then it is P of Mj becomes 1 by m. It is a constant. It is same for all the values of j. That also can be removed. So ML detector, the rule is m cap equal to argument max or maximize Fx of x given Mj. So this is called as a likelihood function that we have already studied. So that is why this is called maximum likelihood detection. Maxima is the likelihood function. Now Fx of x given Mj, you will get it as, so if all the signals are equiprobable, this n0 by 2 ln P of Mj, you get it like this. So Fx P of Mj into Fx of x given Mj, if you take log, you'll get the result like this, that is argument max minus half norm of x minus sj the whole square. So to remove the minus, half is constant, that can be neglected. Remove minus, make it minimum. So minimum x minus sj the whole square. Now this is actually the distance between the vectors x and sj. The square of the distance between the vectors x and sj, norm of x minus sj the whole square. So നേരത്തെ നമ്മൾ കണ്ട ഫിഗറിൽ മിനിമം ഡിസ്റ്റൻസ് ആണ് നോക്കുന്നതെങ്കിൽ ഞാൻ ചോദ്യം ചോദിച്ചായിരുന്നു. മിനിമം ഡിസ്റ്റൻസ് ആണെങ്കിൽ യു ജസ്റ്റ് ഹാവ് ടു assume that if all the messages are having equal probability, then we can use the minimum distance criteria, that is ML detection. Not in this case, not in MAP case. MAP case minimum distance alla, you have to use this equation. But if all the messages are equiprobable, the ML detector reduces to minimum Euclidean distance decoder. So what is the geometric interpretation? We have already discussed it. So the optimum receiver receives the vector x and looks for all sj's that is closest to it using standard Euclidean distance. So it will find the distance between the vector and all the signal points sj, and we will decide that the signal point which is having the minimum distance or which is closest to the received vector is the one that was actually sent. അപ്പോൾ അതാണ് ML detection. Receiver receives vector x and look for all sj's that is closest to it using standard Euclidean distance, and such a detector is called minimum, and we will choose the minimum distance one. So such a detector is called the minimum distance or the nearest neighbor detector. So ML detector in AWGN is minimum distance or nearest neighbor detector. Now the ML decoder or ML detector, it reduces like this. So divide the signal space into m disjoint regions zk, where k is equal to 1 to m. Now the observation vector x lies in region zj if the Euclidean distance x minus sk is minimum for k equal to j. നമ്മൾ ഇതിനെ m regions ആക്കി ഡിവൈഡ് ചെയ്യും. And in each region there will be one signal point Sj, and once we receive a vector, and we will look into that particular region, and we will decide that if the vector is in region 2, then the message 2 was sent. region 1 ആണെങ്കിൽ മെസ്സേജ് പോയിൻ്റ് 1 ആണെന്ന് വെച്ച് നമ്മൾ ഡിസൈഡ് ചെയ്യും. if it is message point 3, if it is in region 3, we will assume that actually the message 3 was sent. So here there is an example. So here you have 4 message points and 2 dimension 5 and 5 2. So message point 1 is this is message point 2, message point 3, message point 4. These are S1, S2, S3 and S4. Now you can see the decision boundary is like this. So this is based on the ML rule, the maximum likelihood rule is the decision boundary. So you can see then the idea is, if for all the points in this region 2, this message 2 is having the minimum distance, the boundaries are drawn in such a way that for all the points in region 2, this message point 2 is, or S2 is having the minimum distance. For all the points in region 1, message point 1 is having the minimum distance, and similarly 3 and 4. So our detection problem reduces to this: find the boundaries of this m decision regions. m decision regionൻ്റെയും m decision region ആയിട്ട് നമ്മുടെ സിഗ്നൽ സ്പേസിനെ ഡിവൈഡ് ചെയ്യാനാണ്, ടോട്ടൽ സിഗ്നൽ സ്പേസിനെ അതിൻ്റെ ബൗണ്ടറി വരയ്ക്കുക എന്നുള്ള ഇതിലേക്ക്, അതാണ് ML ഡിറ്റക്ഷൻ. അങ്ങനെ മാറും. ഓക്കെ, now MAP detector implementation. You'll see how it can be implemented, and the name of that receiver is called correlation receiver. So this is MAP receiver is maximize Cj plus x dot Sj. So we know that what is x? X is actually the message vector or received message vector. So to get x, first you have, this is the vector, x is actually the coefficients of, or the projection of x of t on each of the basis functions 5 to 5t. So in order to get those coefficients, xj is integral x of t into 5j of t dt. So first we will find all the coefficients xj to get the vector x. So x of t, there is an integral and there is a multiplier, so this gives you the inner product. So here you will get x1 integral x of t, phi 2 of t integral x2 and xn, and this will combine all this and you will get the message vector here, or received message vector x cap here. Now you have a correlator, so this will take the dot product. Actually the geometric meaning of dot product is, or dot product in vector space is actually inner product or cross correlation between the two signals in the continuous time domain. We have proved that. So that is in x dot Sj is equivalent to integral x of t Sj of t dt, cross correlation that we have studied before in the signal space lecture. So this will do that. So we'll get x dot s1, x dot s2 and x dot sm. Now you have to add cj. It is also added, and then we will select the largest, maximize, and that is mk. So this is the very famous correlation receiver. This idea. So this correlation receiver is actually implementing our MAP rule. So for ML rule, the Cj reduces to, so for ML rule actually the diagram is the same. There is a change in Cj. In Cj, in ML rule, the Cj, the messages are all equiprobable. So you can use Cj as minus half into Ej. The message probabilities are constant or equal, so that is neglected. So if you are asked to draw the correlation receiver for ML detector, instead of C you can use minus half into Ej. That's the only difference. Now probability of error in correlation receiver. So our optimum receiver, our correlation receiver is our optimum receiver. It is optimum because it gives you the minimum possible probability of error. There will be error, but that will be minimum. Okay, now we will find an expression for probability of error. So suppose that a symbol mj is transmitted and x is received. An error occurs if x does not fall in zj. X falls in some other region except zj, then it is an error. So we are averaging over all the symbols. So the average probability of error is sigma j the probability of the message into the PDF is the average probability of error is sigma j equal to 1 to m p of mj. P of x does not lie in zj given mj. Okay, so it is p of mj. So you assume that all the messages are equiprobable, or we are using ML rule. We are finding it for ML. So it is 1 by m into p of x does not lie in zj given mj. So it is 1 minus sigma j equal to 1 to m. P of x lies in zj mj. It's taking the complement. So what is P of probability that x lies in zj? So in order to find the probability, you have to integrate the PDF. In order to find the probability that x lies in zj, you have to integrate fx of x given mj over the region zj or the whole region zj. The probability കണ്ടുപിടിക്കാനായിട്ട് PDF-ന് എന്ത് ചെയ്യുക, ഇൻ്റഗ്രേറ്റ് ചെയ്യുക. അപ്പോൾ അതാണ് അവിടെ ചെയ്തിരിക്കുന്നത്. So you'll get the expression for probability of error as 1 minus 1 by m sigma j equal to 1 to m integral zj fx of x given mj. Okay. So in the next lectures, we will see some specific communication schemes, or specific passband transmission schemes, and the expressions for, so specific expressions for probability of error.